Hi everyone, my name is Muhammad Fadil bin Jali.
My name is Muhammad Afiq Muhammad bin Ahmad Rizwan.
My name is Wan Najwa Balkis binti Wan Aziz.
Today we will demonstrate how mathematical concept can be applied to design a safe structure playground.
In traditional mathematics education, many concepts are often taught through two-dimensional diagrams and abstract calculation. While students learn formulas and procedure, they may not clearly understand how these mathematical ideas are applied in real-world situations, especially in areas such as engineering or structure design. At the same time, most playground structures are designed mainly for physical activity. Although they encourage movement and play, they rarely take advantage of the opportunity to also function as learning tools that engage students intellectually. To address this gap, our project proposed the design of a pyramid-shaped climbing structure, specifically a tetrahedron, for a school sensory garden. The purpose is to combine physical play with mathematical learning in an interactive environment. In this design, 3D geometry and vector algebra are applied to ensure that the structure is stable, balanced, and accurately positioned. This mathematical concept help to determine the shape, orientation, and structural stability of the climbing frame. Additionally, one triangular face of the pyramid contains a mural. Using vector normal calculations, we determine the correct orientation of this face so that a student standing at the center of the park can clearly view the mural. Overall, this project demonstrates how mathematics can be applied in real-world playground design, turning a simple climbing structure into a meaningful learning experience that connect mathematics, creativity, and also physical exploration.
Okay, now for part 2, coordinate selection. First of all, I will explain how the coordinates for our structure were selected. The aim of this step is to define a stable geometric base for the tetrahedron installation using 3 base points and 1 apex point. Let us start with point A and point B. Point A has the coordinate 730 and point B has the coordinate 370. Both of these points lie on the plane z equal to 0, which means they are located directly on the ground surface. This is important because it ensures that the base of the structure is placed on the flat plane. The distance between these 2 points form a 4-meter baseline. This baseline represents the width of the mural surface. By placing these 2 points on the ground plane, the structure provides a clear and safe area for supervision and movement around the installation. Next is point C, which has the coordinate 220. Similar to points A and B, point C also lies on the ground plane. Since the z coordinate is 0, when point C is combined with point A and B, it forms a triangular base. The position of point C was chosen carefully to create an isosceles triangle, which helped distribute the structure weight more evenly. This design ensures that the base footprint remains balanced and structurally stable. With the 3 points A, B, and C, we now have a triangle base called triangle ABC. This triangle acts as the foundation of the tetrahedron structure. Using a triangular base is very important in structural design because triangles are naturally stable shapes. Unlike squares or triangles cannot easily deform without changing the length of their sides. Now we move to point P, which is the apex or the top of the pyramid. Point P has the coordinate 442.8. The value 2.8 on the z-axis represents the height of the pyramid above the ground plane.
Okay, now let's move on a crucial aspect of our structural integrity, which is the centroid. In engineering, the centroid represents the geometric center of our tetrahedron. It is the theoretical point where the entire design is perfectly balanced. Okay, to find this point, we use the coordinates of our 4 vertices A, B, C and the apex P. By applying the average formula, which is summing up the S and Y components and dividing them by 3, we can identify the exact spatial location of our structure center, which is 4, 4. But why it is important? The position of the centroid directly affects the center of gravity because our pyramid is designed with a wide base and a height of 2.8 meters. The centroid remains relatively low to the ground. This low center of gravity is what gives our wall PVC its anti-tipping property. Even when multiple students are climbing and moving on the mural simultaneously, the weight is distributed toward the base, ensuring the structure remains stable and safe from overturning. This calculation results in a precise balance point at 4, 4, which serves as a structural anchor for the entire pyramid's symmetry.
Next, I will explain how the dot product is used in our design to ensure the stability of the structure. In structural engineering, a structure is most stable when its vertical height is perfectly perpendicular to the ground or its foundation. This means the force or weight of the structure is transferred directly downward into the ground, which help prevent instability or uneven stress. To verify this mathematically, we use the dot products of vectors. First, we define the altitude vector, which represents the vertical height of the pyramid from the base to the top point. In our design, this vector is represented as MP, which equals 0i plus 0j plus 2.8k. This shows that the height is purely vertical in the z directions. Next, we define the base vector, which represents the horizontal foundation of the structure. In this example, the base vector AB is negative 4i plus 4j plus 0k. This indicates that the base lies entirely on the horizontal plane with no vertical component. To determine if these two vectors are perpendicular, we calculate the dot product between vector MP and vector AB. When we multiply the corresponding components and add them together, we obtain a dot product of 0. A result of 0 means that the two vectors are orthogonal, or in other words, perfectly perpendicular. This confirms that the vertical height of the pyramid is perpendicular to its base. As a result, the load of the structure is transferred directly to the ground, improving structural stability and long-term safety. Therefore, the dot product provides a mathematical proof that our design follows an important engineering principle for a safe and stable climbing structure.
In this section, we verify whether the installation forms a true three-dimensional tetrahedron. To do this, we use a mathematical method called the scalar triple product. The purpose of this calculation is to check whether the points A, B, C, and P lie on the same plane or form a real 3D structure. If the result of the scalar triple product is 0, it means the vectors are coplanar. And if the result is non-zero, it means the vector forms a three-dimensional solid. Okay, in the first step, we construct vectors from the coordinates of the points. For example, we calculate vector AC by subtracting the coordinates of P from point A from point C. In a similar way, we construct other vectors, which is vector AB and AP. These vectors represent the edges of the tetrahedron in three-dimensional space. Next, we apply the scalar triple product using a determinant. The determinant is formed using three vectors, vectors AB, AC, and vector AP. This determinant helps us compute the volume of the tetrahedron. Now, calculate it. The determinant is written in the matrix form. By expanding the determinant step by step, we obtain the final numerical result. After performing the calculation, the value obtained is 67.2. The determinant value is now equal to 0. A non-zero scalar triple product means that the vectors are linearly independent. In geometric terms, this means that the point P does not lie on the same plane as the base triangle ABC. Therefore, the structure forms a true three-dimensional tetrahedron, not just a flat shape. The scalar triple product also represents the volume of the tetrahedron. This confirms that structure has real 3D space and height.
Okay, now we will dive deeper into a mathematical foundation of our project, the base area calculation. For a structure like wall PBC, the footprint is everything. We need to prove that the base is large enough to distribute the total load of the structure and the students effectively. To determine the area of the triangle base formed by vertices A, B, and C, we apply the vector cross product theorem. By defining two vectors A, B, and AC from our fixed coordinates, we can calculate their cross product. This operation gives us a vector that is perpendicular to the base, and its magnitude represents the area of a parallelogram. However, since our base is a triangle, we take exactly 1/2 of the magnitude. Mathematically, the formula is 1 over 2 modulus AB cross product AC. With our cross product magnitude resulting in 24 units, we arrive at a base area of 12 square units. This substantial surface area is what provides the stability zone. The base acts as a heavy anchor concentrating the mass closer to the ground, which minimizes the sway and vibration when the climbing wall is in use.
Next, I will explain the surface area analysis of one triangular face of the pyramid structure. To calculate the exact surface area of this triangular face in the three-dimensional space, we use the cross product of two vectors. The vectors we use are AB and AP, which both originate from point A. These two vectors represent two sides of triangular face. The first step is to compute the cross product of vectors AB and AP using the determinant method with the unit vector I, J, and K. After performing the cross product calculation, we obtain a new vector that is perpendicular to the plane formed by AB and AP. Next, we calculate the magnitude of this cross product vector. The magnitude represents the area of the parallelogram formed by the two vectors. However, since our surface is a triangle, we take half of that value. By using this formula, we obtain a final triangular surface area of approximately 8.87 square meters. This calculation is important for two reasons. First, the result shows that the mural surface is large enough to act as a clear visual focal point for students in the sensory garden. Second, knowing the exact surface area helps with accurate budgeting and material planning, such as determining the amount of paint or materials needed to create the mural. Overall, this analysis demonstrates how vector mathematics and cross-product calculation can be applied in real design situations, helping ensure that the structure is both functional and visually engaging for students.
Okay, now I will analyze on mural orientation. Our goal is to mathematically determine how a mural on the pyramid surface is positioned relative to an observer. To do this, we use the coordinates of the pyramid and the position of the viewer to calculate whether the mural is facing the observer or facing away. Refer to the diagram, we have a primary school student named Muhaimin, who is standing at the center of the park. Muhaimin's position is defined by the coordinates 10, 10, 1.4. The 1.4 represents his height in meters, which is where his line of sight originates. He is looking toward a specific triangular face of the pyramid, labeled as wall PAB. In the diagram, we can see two important arrows. The normal vector N that shows which way the wall is facing, and the viewing vector V, which represents the direction of Muhaimin's gaze. To solve this mathematically, we first need to define our vectors. First, the normal vector. The normal vector of the mural is derived as vector n equal to 11.2i plus 11.2j plus 8k. This vector is perpendicular to the wall surface. It tells the outward direction of the mural. Second, the viewing vector. In step 2, we calculate Muhaimin's line of sight. We take a point on the mural, point P at 4, 4, 2.8, and subtract Muhaimin's position, 10, 10, 1.4. This gives us vector V equal to negative 6i minus 6j plus 1.4k. This vector represents the path of the student's eyes to the mural. Now, how do we know if they are facing each other? We use the dot product by multiplying the components of the normal vector and the viewing vector. We get the result is negative 123.2. In vector mathematics, the sign of the dot product is the most important clue. Because the result is negative, it provides definitive proof that the two vectors are pointing toward each other. The calculation confirms that wall PAB is in a face-to-face configuration with Muhaimin. The mural is not hidden or parallel. It is perfectly oriented for the student to view it.
Okay, to determine the precise slope of wall PAB, we begin by identifying two position vectors, AB and AP, which define the surface of the wall. By performing a cross product on these vectors, we calculate the normal vector, essentially the perpendicular anchor of the plane. From there, we use the dot product between this normal vector and the horizontal ground plane to find the angle of inclination. The result of this calculation is 63.2 degrees. By using a slope instead of 60-degree vertical wall, the weight of the mural and its support beams is naturally directed downward and inward toward the centroid. This mathematical result proves that the structure is self-stabilizing, which is the wall effectively uses gravity to to press itself into the base, significantly reducing the risk of tipping. For a child standing in front of the mural, this angle reduces the distance between their eyes and the topmost content without causing neck strain. It also ensures that the magic of math isn't just a wall, but an accessible learning interface where every equation is within a comfortable field of vision. In summary, our vector calculations aren't just numbers on a page. They are the proof that the wall PAB is engineered for structural permanence and visual accessibility, creating a safe and effectively educational environment.
Next, I will explain the mathematical discovery design, specifically the mural placed on wall PAB of the pyramid structure. This triangular wall is designed to display a mathematics-themed mural that students can easily see while playing in the accessory garden. The mural includes colorful elements such as number, basic equation, shapes, and clocks, which help introduce mathematical ideas in a fun and engaging way. The purpose of placing the mural on the playground is to show students that mathematics is not only something they learn in the classroom, but something that exists in the real world around them. By integrating mathematical visual into a play environment, the space becomes both educational and interactive. Another important idea behind this design is passive learning. Even when students are not directly studying the mural, their brains are still observing and absorbing the information while they play, walk past the structure, or rest nearby. This means that students are constantly being exposed to mathematical concepts in a natural and enjoyable way, which can help improve their familiarity and confidence with mathematics over time. Overall, the mural transforms the climbing structure into more than just playground equipment. It becomes a visual learning tool that encourages curiosity, creativity, and also discovery, which helping students see mathematics as something fun, meaningful, and connected to everyday life.
Next, I would like to direct your attention to the design of the climbing wall and PBC. This section is aimed to bridge the gap between abstract classroom, geometry, and physical exploration. The primary objective of wall PBC is to reinforce a student knowledge of polygonal geometry through kinesthetic learning. Instead of just looking at shapes in a textbook, students are required to physically interact with them as they scale the wall. As they climb, they move through a progressive sequence of geometric polygons, beginning with the simplest form at the base, that is triangle, and advancing upwards through increasingly complex shapes such as square, pentagon, hexagon, and all the way up to the decagon at the peak. This physical engagement allows students to literally feel the properties of each shape, such as the numbers of sides and vertices, making the learning process much more memorable and intuitive. By turning a playground into a living classroom, we transform geometry into an adventurous challenge. This climbing activity doesn't just build physical strength, but it also builds a strong mental foundation in spatial awareness and shape recognition, proving that mathematics is not just numbers on a page, but a world we can explore with our own hands.
Okay, next is wall PAC, which serves as the designated descent zone. This surface features a numerical rope ladder specifically designed to turn the act of climbing down into an interactive learning experience. The key advantage of wall PAC is the kinesthetic learning. As students descend, they practice backward counting from 10 down to 1. By physically moving from one step to the next, students internalize the concept of descending sequences and subtraction through the direct physical action, making the lesson far more memorable than traditional classroom learning. In short, wall PAC transforms the descent from the apex into a controlled educational journey blending physical play with the fundamental mathematical logic.
The conclusion is, this project has transformed my view of 3D geometry from abstract theory into a practical tool for inclusive design. By defining the structure with coordinates like A730 and the apex P 442.8, we realize that every point in a 3D system dictates a student's safety. The vectors approach was the most effective way to prove the design's integrity by using the normal vector, allowing me to mathematically guarantee that the slope will enhance visibility of student. This proves that math is not just a set of calculation, but a vital problem solving tool for creating safe, evidence-based learning environment. As a future teacher, we plan to use this experience to show my students how mathematics acts as a living tool in the real world. This project has empowered us to become a better educator who can bridge the gap between complex mathematical concepts and meaningful, safe, and accessible classroom design. That's all from me and our group. Thank you.